Good afternoon. My name is Jieun Kim from OS Lab at KAIST, and today I'm going to present OPIMQ, an order preserving I/O stack for multi-queue block device. Here's what I'll cover today. I'll start with why storage order matters, explain the problems with existing solutions, introduce OPIMQ, and wrap up with our evaluation results and key takeaways. Modern storage systems adopt multi-queue architectures to efficiently process parallel I/O requests. At the OS level, multiple request queues let each CPU core submit I/O separately, avoiding contention. At the device level, multiple command queues, such as those in NVMe and UFS, help fully utilize storage bandwidth. When an application issues a write, the request travels through the request queue in the host site before reaching the storage device. In a single queue system, all requests are processed sequentially, naturally preserving order. But in multi-queue systems, requests are distributed across multiple request queues. Each request queue then dispatches its request to each corresponding command queue. The distributed I/O at the command queues can be reordered by the storage controller or FTL. As a result, the modern I/O stack is inherently orderless, as requests may be completed in a different sequence than they were issued. Applications are responsible for enforcing write order, known as storage order, the sequence in which data becomes drawable in storage. In database logging and file system journaling, enforcing storage order is needed to ensure durability and correctness in the event of a crash. Applications must enforce a storage order using costly mechanism. To ensure the writes are drawable in the correct sequence, an application must wait until all preceding writes are fully persisted before dispatching the next one. This strict enforcement limits parallelism and increases latency. The cache barrier command offers a more efficient way to enforce storage order. First introduced in 2005 as part of eNMHC storage, the cache barrier command guarantees that writes become drawable in order. With a cache barrier, even if writes are dispatched sequentially, following writes cannot be drawable until all preceding writes are fully persisted. This prevents out-of-order durability, reducing the need for applications to enforce storage order manually. To reduce the overhead of enforcing order, several approaches have been explored, which can be broadly classified into two types. The first is in-order writes, where writes are performed sequentially using a cache barrier. The second is out-of-order writes, which initially write data without order and later recover the correct order in the event of a crash or a system failure, using global write identifiers or PMR in NVMe. While these methods help enforce storage order, they have significant limitations. Barrier I/O stack works only on single queue devices, making it incompatible with multi-queue storage architectures. Lazy barrier is restricted to UFS, and OPTR supports only a single write stream. Hooray, CCNVMe and RIO require specialized hardware resources or rely on inefficient ordering mechanisms. These limitations highlight the need for a solution that efficiently enforces the storage order in multi-queue storage systems. Now, I will outline the problems we aim to solve. This slide illustrates the core problem. In a single queue I/O stack, a cache barrier naturally preserves the storage order. However, in a multi-queue I/O stack, dependent write requests may be distributed across different queues, allowing the storage controller to reorder them. This can cause a following write to reach the storage media before an earlier one, breaking the expected order. Even with a cache barrier, storage order may still be compromised in multi-queue systems. To understand the problem in the multi-queue system, we define two key concepts, stream and epoch. A stream is a set of I/O requests issued by a single thread. Within a stream, an epoch is a group of write requests that can be reordered internally but must be persisted in creation order. Each epoch is delimited by a cache barrier. The core issue is that storage order is not naturally enforced between write requests in different queues. Enforcing order becomes challenging when requests with dependencies are assigned to separate queues, a problem we call inter-queue storage order. This occurs in two cases: when dependent requests come from the same thread or different threads. The first challenge is guaranteeing intra-stream storage order. With core migration due to work stealing, write requests from a stream may be distributed across multiple queues, causing epoch split, where requests from the same epoch end up in different queues. As a result, the cache barrier may reach the storage controller before other requests in the same epoch, prematurely delimiting the epoch and misplacing requests, compromising the storage order. The second challenge is guaranteeing inter-stream storage order. When write requests with ordering constraints originate from different threads, especially on separate CPU cores, each thread registers its write request in its assigned queue, requiring the system to enforce order across queues, potentially compromising the storage order. To address these issues, we introduce OPIMQ, an order-preserving I/O stack for multi-queue block device. This is the key concept of OPIMQ. OPIMQ ensures storage order through collaboration of host and storage. At the host level, each I/O request is assigned a pair of stream ID and epoch ID, defining its ordering constraints and passing them to the storage. At the storage level, these IDs enable correct persistence order even across multiple queues. This is a design overview of OPIMQ. At the host level, the order-preserving file system determines the placement of cache barriers according to ordering constraints. OPIMQ structures I/O requests into streams and epochs, assigning each request to the corresponding IDs. At the storage level, OPFTL ensures epoch-based persistence order, while dual-stream writes and sibling-aware delayed mappings guarantee inter-stream storage order. In OPIMQ, write requests from the same thread belong to a single stream. The stream ID is derived from the thread's process ID. Within each stream, epochs are delimited by cache barriers and assigned unique identifiers. The block device layer assigned a pair of stream and epoch IDs to each I/O request. Now let me explain how OPIMQ addresses the first challenge, guaranteeing intra-stream storage order. To prevent epoch split, OPIMQ introduces epoch pinning, ensuring all writes in the same epoch are placed in the same queue. If a thread migrates before epoch delimitation, it dispatches write requests to its original queue. New requests are placed in the migrated core's queue only after the cache barrier delimits the epoch. This prevents premature epoch delimitation at the storage level. The second challenge is ensuring storage order across threads, which requires preserving the order between epochs from different streams. OPIMQ introduces dual stream write, a write request that belongs to two streams simultaneously. When enforcing inter-stream order, OPIMQ designates writes from the preceding epoch as dual stream write. For example, in the diagram, epoch 12 from thread A must persist before epoch 6 from thread B. To enforce this, OPIMQ marks W1 and W2 as dual stream writes, meaning they belong to epoch 12 in stream A, while also being part of epoch 5 in stream B. A dual stream write carries two pairs of stream and epoch IDs. In addition to its original stream and epoch ID, it is assigned a secondary stream and epoch ID. In the diagram, a write request in epoch 12 of stream A is marked as a dual stream write, carrying two pairs of IDs, stream A, epoch 12, and stream B, epoch 5. OPFTL ensures writes are persisted in epoch order within each stream by referencing the stream and epoch IDs in the request. The key idea is that data can be flushed to the flash media in any order to maximize parallelism, while the mapping table is updated strictly in epoch order. Now, let's see how to enforce inter-stream storage order. A dual-stream write carries two pairs of stream and epoch IDs representing two ordering constraints. OPFTL interprets these constraints and persists the write only when both conditions are met. If only one condition is met, OPFTL delays the mapping update until both are satisfied. This is called Sibling-Aware Delayed Mapping. In the top diagram, a single stream write A5 has only one ordering constraint, so each L2P mapping is updated in the table immediately after A4 is persisted. In the bottom diagram, the L2P of the dual stream write remains delayed, even if A4 is already persisted. The mapping is updated in the table only after B10 is persisted, thereby ensuring inter-stream storage order between stream A and stream B. Now let's move on to the evaluation. We tested all workloads on a 40-core server with a Samsung 980 Pro as the storage device. OPIMQ is implemented in the Linux kernel. For evaluation, we selected ext4 as a representative file system and referred to it as OPExt4 throughout our experiment. We compared OPIMQ with three configurations: ext4 with legacy IO stack, barrier IO stack with a single command queue, MQFS in CCNVMe. First, we compare fsync latency between OPExt4 and the legacy ext4. When fsync is called in ext4 journaling, file data and journal log blocks must be written before the journal commit block to maintain consistency. To enforce this order, the legacy ext4 waits until file data and journal logs are fully written to the storage device before dispatching the journal commit block. OPIMQ eliminates the DMA transfer delays and the overhead of fua flag associated with enforcing this order. As a result, fsync latency in OPExt4 is reduced to 1/3 of that in ext4. For the macro benchmark, we evaluate OPIMQ in a cloud environment using Filebench varmail, dbench, and sysbench OLTP insert. We measure IOPS while increasing the number of running containers to assess scalability. OPIMQ outperforms the vanilla Linux IO stack 2.9 times in varmail, 2.8 times in dbench, and 2.9 times in sysbench. We also measure the overhead of epoch pinning across benchmarks, running 40 concurrent Docker containers executing workloads simultaneously. The results show that epoch pinning has minimal impact on performance, demonstrating its efficiency in managing ordering without significant overhead. Finally, the overhead of OPFTL is as follows. We use Cosmos OpenSSD board and generate the 4 kilobyte random write followed by fsync. The overhead of ensuring the storage order in OPFTL is negligible because it can flush the write-back cache in any order while preserving the mapping update in order. With this design feature, OPFTL can ensure the storage order among the epochs while fully exploiting the internal hardware parallelism inside SSD. I will now go over the conclusion. In summary, OPIMQ enforces storage order in multi-queue block devices by coordinating between the host and storage. It preserves both intra-stream and inter-stream order using epoch pinning and dual-stream writes. OPIMQ opens up a new avenue for the cache barrier command to be employed in the general storage product. OPIMQ is open source, so feel free to test and explore it. Thank you very much.